2, 1. All right, so repeated sampling in a normal distribution. So I'm going to assume that, of course, you are familiar now with the normal distribution. I'll put up a link up above there to the original video on normal distribution. And you can watch all kinds of examples on this channel if you wanted to. The main idea here is that we, next to never, okay, basically we'll sample the entire population for some characteristic that we're interested in, So if we're trying to sample, we're not going to be able to take the entire thing. So what happens? Well, we start taking samples which are much smaller, so maybe 10, maybe 20, if we're lucky, 100, 1,000. So the more samples we have, the better approximation, okay, of that characteristic within the population we're going to get. So that's not really surprising. So obviously we would want to have as many as we can. But what if we, can't have thousands and thousands of these samples? Well, then what scientists will typically do, they'll try to do repeated sampling. Now, what does this mean? So if you take the entire population and you're stuck, okay, that you can't sample across the whole thing, you can imagine that, you would have, let's say, a sample, okay, and this would be your sample number 1 of, let's say, and you're sampling across n kind of elements for the characteristic you're looking for. Now, n can be 10, can be 20, can be 100. Okay, so now if we do that, then of course, so from here, from this, we can calculate what our mean is. Now, because we're talking about a sample here, so it'll be, x bar. And then we can calculate our standard deviation. So in our standard deviation, I'll just designate as S for the sample instead of the sigma. And this would have been, let's say, I'm going to call this number 1 because it's from the first sample, right? And we took n items. Now, what you might do is you might say, okay, well, I want to take another sample, and this would have been sample number 2, and you're still going to take n items. Now, they're not necessarily the same n items. You would just sample randomly, right? So the idea is you would sample n random items again, and this, again, you could calculate what your mean is. I'm going to call this number 2, and then what your standard deviation is for this sample, right? So now we would have 2 different samples. They have exactly the same number of elements, and then we're pulling out some characteristic that we're interested in. Now, we know ahead of time that the population is normally distributed for that characteristic. Now, for sample 1 and sample 2, the likelihood of them having the same mean, okay, I mean, they could, but, it's not going to be exactly, right? So the probability of having the exact same mean is not going to be the same because of the fact, that we're not sampling the whole population. If we were sampling the whole population, we didn't need to have multiple samples within here. And the same thing would happen for your standard deviations. Your standard deviations may not always be the same. And if you would continue this, so you can continue this as many times as you like, so say sample number 3, sample number 4, number 5, and you go on like this. Okay, now of course, okay, you're not going to do it for an infinite amount of times, but let's assume that you did. Well, then what you would have is you would still continue to be sampling this, okay, at n, and then of course you're going to get some, okay, x, okay, and then you're going to get some standard deviation. Now, all of these, okay, would have been different. Now, it turns out that it has been shown, what's pretty neat, is that all of these, all right, so if you took all the samples that you had, and they have a certain mean, and then they have a certain standard deviation, what you would notice is that through all of this repeating samples, okay, this data, let's say you had, mean number 1, mean number 2, mean number 3, and so on, across all the different samples that you took of these n elements, okay, all the way, continuously. So what turns out that this is also normally distributed. So it also has this, okay? So it has this structure as being normally distributed, okay, across all the different means. Moreover, it turns out that if you took, okay, the mean, okay, of all of these, now you, again, this may not surprise you, but you could probably take a guess. What would have been the mean of all the means of the samples? Well, if you were doing it with regards to the population, okay, the mean that you had across all of these different samples actually turns out, of course, to be mu of the original population. And that's not really a surprise. Now, you also can see, okay, if you would do this, okay, that the standard deviation, okay, that you would have, so if you took the standard deviations across, okay, and then you would have this mean, what would have been the standard deviation now across all the different means, right? So each sample would have had something different. But if you took the whole thing, okay, and you took all of your means, and now you took the standard deviation of those means, you know what it turns out to be is that your actual standard deviation, okay, so with respect to all of these samples, turns out to be your original standard deviation divided by the square root of your sample size. So if your sample size was 1, right, if you took, then the standard deviation would be just sigma, right? Because you're just sampling one element at a time from this whole population, and you have done it infinite times, so you're basically just doing the whole population. But, okay, our standard deviation, okay, with respect to all of the means, okay, as n increases, so, as it goes to 2, as it goes to 5, 10, 100, okay, you will notice that this standard deviation, okay, becomes smaller and smaller, so it becomes narrower and narrower. So what we have is that, this is going to start looking something like this, all right? So it's going to go in this way, where your mean, okay, across all of your means, okay, of the samples is going to be mu, okay, so that's 1. And then your standard deviation, all right, so within the first 68%, okay, of data, so it turns out that this is going to be sigma all over square root of n. So sigma over square root of n. And the bigger the n, okay, the more clustered that these items are going to get, so this is going to just keep blowing up in here, okay, as n gets bigger and bigger, because the sigma is going to is fixed, and then the square root of n, okay, forces this fraction, okay, to narrow this down further and further, so you have more and more data within. Again, not a surprise, because if we have more, if n goes on to infinity, so if it gets bigger and bigger and bigger, we basically will approach the entire population. So the bigger the sample size, the better we can figure out what the characteristic that we are looking for. So this has been shown, and it's really neat. And we can play on this now, okay, and then calculate probabilities, okay, with respect to maybe some sample. So, for instance, how would you use this now? Okay, if you were doing this, okay, so these repeated sampling. So let's say we have something like this. Now, I did an example with regards to birth weights or birth mass, okay, to be exact specific, where birth weights, okay, so babies coming in to the world is 3,500, okay, or 3,514 grams. And then the sigma is 385 grams, right? And birth weights are normally distributed. Now, if you want to see the full example of this and the calculations, I can put up the link to all the different examples I did for normal distribution. But in here, okay, there's an interesting question that I want to be able to apply to this repeated sampling. Now, it says that, how probable would it be that a hospital baby unit would have a mean of 3,380 grams or less in a sample of 20 births? So here's the mean, right? So our mean is this, okay, that we have, and we want to see how would it be, and our sample size is 20. And you can imagine, so let's say maybe it's on a weekly basis, they're just continuously, having, I'm not saying that it's always 20, okay, kids that get born, but let's say on a weekly basis, maybe it's 20, and then another 20, and another 20. So it's like sampling on a continuous basis, forever, and then seeing what happens. So within here, if I would take this in here, I'm going to copy this down. So let me copy this. Okay, bring it down. Okay, right here. So what we're doing, okay, so I can erase all of this stuff, is that we know, okay, that if we were repeatedly sampling at 20, our mean would have been the same thing, right, as our original population. So let's say if this was it, that's our original mean. And now for a sample of 20, then our standard deviation becomes the original standard deviation of the entire population divided by, okay, the square root of your sample size, which in this case is 20. So if I do that, let me pull up the calculator here. So divided by square root of 20. So that would have been 86, okay, let's say 0.1 grams, all right? So what that means that within that 86.1 grams, 68%, right? So from the right and to the left, 68%, okay, of all the samples that would have been at 20, okay, so 20 samples, would fall within that close to your original mean of 3,514. And now what this is saying is that it's saying, well, in that particular sample of 20, okay, how probable would it be that we would fall all the way at 3380? Now notice 3380, so it's going to be far off here on the tail end, somewhere over here, 3380. So the probability of having a sample of 20, right, babies, and then having their mean, so this is their mean, being equal to this, okay, or less, okay, so it says or less. So having that probability is going to be very small, okay, if you had 20 babies, okay, that were born. And now, of course, we can calculate this. So, I can figure this out. So let's say, I can use the z-score in here. So we would have, okay, so this is 3380. So that is my, my x, okay. Okay, this is the entire mean, and then my standard deviation, okay, and this would have been 86.1. So this is going to give us some negative value here. So let's see, 3380 minus 3514, and then my answer divided by 86.1. So this is negative 1.556, okay, or approximately negative 0.1. Okay, let's put it at something like that. Okay, so this is approximating, and now I can use my z-scores. Let me go back, find the table. So here's my table in here. So negative 1 point, actually I can go to 2 decimal places within here. So let's keep it at negative 1.56. All right, let's find that on our z-score table. So negative, let me erase this junk here. So there is negative 1.5. All right, and then we are looking for 5. So this would have been, that's this column right here, and then all the way across here. So that is 0.06057. So 0.0, let's say 6. Okay, so this is probability 0.06, okay, approximately. So that's the probability of having, okay, these to be less than, okay, or equal to 3380. And of course, you can utilize Desmos, okay, as a check. You can utilize a graphing calculator. But this tells us that it's approximately only 6% probability that if you took a sample of 20, okay, babies, and then you had a mass of 3,380 or less, okay, very low probability of that. So that's how we can utilize this, okay, and then in comparison to the entire population. And then we can do all kinds of tests, right? So this is really neat. Now let me just double check. Okay, I'll pull up Desmos. Okay, so in Desmos, so normal distribution. So in this case, we have, this is 3,514. So that's that. My standard deviation was 86.1. All right, and then now I want to find my cumulative, so I'm going to hit that, and then my maximum was 3,380. Okay, so there you go. So 0.0598, so 6%, which is exactly what we got from our Z-scores in our table. So this is really interesting to be able to do. So that's what happens when you are doing repeated sampling. All right, so you can find out what your means are, and then you can use that data, okay, to solve pretty interesting questions like this. What's the probability of something having a mean in a sample? All right. Okay, so thanks for watching, and we'll see you in a future video. Bye, everybody.